today we're talking about the dual nature of light. All right, dual nature of light. Dual meaning two, so is it a wave or is it a particle? It's dual nature of light. So, like I said, light, is it a wave or a particle? We're going to talk about some evidence that supports that it's a wave. Okay, there's different characteristics of light that would make it like a normal wave that we've talked about before. Some examples are reflection. So it actually goes through the process of reflection. If light hits a boundary, it's going to hit and bounce off. The process of reflection occurs with light. Also refraction. Okay, we talked about that a little bit more detail in the last video. If here's the normal, it's going to go there. It's going to bend towards or away from the normal. So we'll go through the process of refraction. If you want to draw on these pictures, feel free. Diffraction. Okay, we've talked about diffraction before too. If we have a wave front moving towards, okay, if it's moving towards something like this, once it gets on the other side, it's going to bend. All right, so diffraction is another example of a wave behavior that light undergoes. Interference. We've also talked about interference before. Something's coming this way, something's going that way, and that can interfere. Kind of cancel each other out. It could be constructive or destructive. All right, so interference is another example of wave behavior. Okay, these are all examples we talked about. So kind of had a question for you here. Where do we observe these phenomena? Some answers would be the Ripple tank. We looked at all of these really. We looked at some different, in our sound lab we ran into some of these. So we'll talk more about this with light as we go forward, but we've actually seen these wave behaviors in other experiments already. All right, polarization. We just discussed it quickly. We'll talk more about it as we go here. We discussed it also in the last video. So polarization, as far as in the real world, where do we observe this? We have our polarized sunglasses, but also just a reminder, we'll discuss that a little bit more as we go forward. Now, so light, wave, or particle. Now let's talk about some evidence that supports that it's a particle. Okay, in other words, waves would not do some of the things we're fixing to talk about right now. Okay. Physics has yet to explain the following as of 1900. So a little over a century ago, they couldn't explain why these things happen. We've learned a little bit more about what's going on, but still, these once again defend particle over wave. Okay, atomic spectra, right, and we'll go into more detail and over all these in a second. Okay, atomic spectra is a characteristic color pattern. Okay, so every object has a different color pattern. Okay, we'll discuss what that means more in just a second. All right. Black body radiation. All right. The black body radiation is actually the absorption and emission of energy. Okay, and what kind of energy are we talking about? We're talking about light energy. As we mentioned in the last video, we're talking about photons, packets of light energy. Okay, and the photoelectric effect, photo emission of electrons. Okay, because we'll talk more about this in a second too. Photoelectric effect has to do with shining light on something, and actually it's going to cause the release of electrons. So we'll talk more about that in just a second. All right, so as I said before, every element has its own signature emission and absorption rate. Okay, I was going back and forth on whether I was going to have you draw this or not, because the emission and absorption are pretty much the opposite of each other. All right, so as you can see over here, this hot gas and this cold gas, they're the same gas, so this is the emission and absorption spectrum. And as you can see, you kind of see the parallel here. That's the spot there. That's the same spot, same. So really, but what's interesting about these two things is both these depend completely upon what the element is itself. Every element is going to be slightly different. That's how we can tell what elements are different places, including in astrophysics out in the space and those kind of things. All right? So every element has its own signature emission and absorption spectrum. And we'll talk, you're probably most familiar with something like this. This is the continuous spectrum. If I shine a white light through a prism, it's going to break apart into all the different types of light there is. That's called a continuous spectrum. Now, black body radiation. A black body is an object or system that absorbs all radiation which it comes in contact with. All right, so all radiation. Okay, we talked a little about electromagnetic spectrum. There's definitely different types of radiation, such as your gamma rays, your X-rays. So all of that would be absorbed by a black body. Now, black body radiation is the radiation emitted from a black body. Okay, and what's interesting about this, we won't go into this in a lot of detail, but it's actually, we only can tell this by the temperature. Okay, it's usually associated with stars. We can measure the temperature, but not the radiation levels. We can't tell exactly how much radiation is given off, but we know that so we can measure the temperature of it, though. Thought that another example there. Okay, another thing I just want to remind you, energy is quantized. Okay, we talked about photons last week. We're going to talk a little more about how that has to deal with light. So energy comes in discrete units called quanta. Okay, when we talk about light, we're talking about photons. Remember, we said photons are massless bundles of energy, right? Yeah, I think in the other video I may have referred to it as like packets of light energy. Okay. Those are photons, okay, packets of light energy. They kind of group together. They're very discrete units. In other words, you can't really separate them. You can only separate them so much. There's still going to be a certain little pack there. And this understanding of quanta is what leads us into something called quantum mechanics, which we're going to talk more about in a second. Oh, there it is. I forgot I left on the side. So this actually is the birth of quantum mechanics, which I've kind of written all over there. Okay? There it is, okay? Birth of quantum mechanics. We'll talk more about that. What that means is we have our basic understanding of physics, and then now we have started to find some answers. We can't find some answers, and you find something called quanta with the photons, and that's actually how you begin the understanding of quantum mechanics, which is a lot of modern physics. But this is the one I really want you to draw, because this is one that's really important for you to know, and we'll talk more about it in class together, and probably do an example virtual activity or something like that to make sure you understand it. So I already have the sodium metal on the paper for you. The big thing here is make sure you label these. You have light photons, okay? So once again, here's a packet of light, packet of light, packet of light. You get the idea. And that hits the metal surface. Now, because of this added energy to the metal surface, it actually starts to release or emit the electrons from the surface. Okay, so once again, if you're labeling this picture, these are going to be the electrons. All right, you see after the energy is added from the light, you're actually going to see electrons emitted. If you need to pause it, give yourself a little bit more time to draw a picture, that's fine. Go ahead and do that. All right, now we're talking a little bit more about the photoelectric effect. I just want you to see some of the difference. This would be classical physics, okay, or what we consider light as a wave. Just kind of fill in this chart here. So whether electrons are ejected depends on, you would think it would be the intensity of the light. So therefore, if you have more intense light, then it would eject faster or eject more, that kind of stuff. But it turns out that it depends upon the frequency of the light. So how often the light's given, and those kind of things. The kinetic energy of ejected electrons depends on, once again, in your regular understanding of classical physics, you would think it's the intensity of the light. Okay, but going through different studies and experiences that have been done, it's actually, once again, the frequency of the light. Right, we'll talk more about what that frequency is in just a second. At low intensities, electron ejection, you would think would take time. So therefore, if it's a low intensity, it would just take, be very slow. What actually happens is, if you get to a certain frequency, it's going to occur almost instantaneously. So before that frequency, it doesn't occur, but as you get to that frequency, suddenly the electron ejection or emission or release starts happening a lot. Okay, the important of this experimental data is this actually, once again, supports the duality of light, because this supports light as a particle. Okay? Now the photoelectric effect in a little more detail, classical versus quantum. We're not going to make you write all these down, just kind of some good information here. These observations support light being a particle rather than a wave. It requires electromagnetic energy be quantized. Okay, back to that quanta, which is the photon, as the guy named Max Planck proposed earlier, or Planck, some people say it, his explanation of black body radiation, okay, which we mentioned just a little bit. Now, a guy named Albert Einstein, most of you guys probably at least heard of him. He extended Planck's quantized energy to a stream of photons. So he actually he furthered it and gave us an understanding of the stream of photons, such as we drew in the picture just a while ago. A work function, the definition has really just the minimum amount of energy required for an electron to escape. So in other words, once again, you have to add energy. What does it is? Energy must be added to release electrons, okay? Now the value of the work function depends only on the metal. That's really important. Like I mentioned before, there's a certain emission spectra, a certain absorption spectra that's dependent just on the metal, but also it's just dependent in the work function here. The amount of energy required is dependent upon the metal. All right, that's the only thing you need to we'll elaborate more on that in class, but the only way it's going to change is if it actually changes the type of metal it is. The type of metal it is what affects how much energy is required. Let's see. So this is one of the big things you want to talk about, threshold frequency. Okay, we mentioned a while ago in that experimental data, the frequency over and over again. The frequency of incident radiation, okay, which we're talking about light, so it's going to be the photons, below which there is no ejection, okay? No ejection of electrons. So if you do not reach this frequency, then there will be no ejection of electrons from a metal. Okay? We typically do that as F sub t, so because that's threshold frequency, the units are in hertz there. So let's say the threshold frequency was 102 hertz. All right, if you have the light being emitted at 100 hertz, then you would have no ejection, no release of electrons. You have to get to that threshold in order to begin releasing the electrons. This kind of summarized photoelectric effect. We already drew a picture of it. This would kind of be what some people learn better by seeing it in words and looking at it. So light is going to hit the metal. Okay, so it's pretty obvious light's going to have to hit the metal. If the frequency of the light is above the threshold frequency, okay, really at that or above, then the loosely bound electrons will be emitted, okay, or released from the metal. We'll talk more about loosely bound because there's certain electrons that are released more easily. Also, with that, metals with more loosely bound electrons will have a lower threshold frequency. So in other words, they're more ready to get rid of those electrons. So it'll require less energy. So if you have a lower threshold frequency, then you would require less energy to release those electrons. That makes sense. That kind of goes with the work function understanding of threshold frequency. Okay, this is a little more complex because this is starting to get into some of the modern ideas, but photoelectric effects are really important because we can do different things with that in the real world. All right, hope you enjoyed.